Look,
Yeah.
I'm a boy now.
What the f?
I'm a boy now. Yeah,
Oops, I was supposed to show that. It's my first stream on. It's not my first stream on YouTube, but I want to make sure I'm doing it the proper way. Let me see. Yo. Let me see. Yo. 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 Why does the quality look so bad? That's not even how my game looks. I mean, that's not how my shit looks. Is it really that bad? Oh, doesn't look bad. Why is this so bad? Why is this so bad? Oh, it's good. Oh, it's good. The quality is going down because of if I do that, you see it's good. Okay, good. If I do that, you see it's good. Okay, good. Okay. Okay. Save that for now. Let's put some music. Okay. I already did some studying in the beginning. And this is chemistry, starting off with chemistry. I'm gonna start studying for hopefully 3 weeks. Starting for the MCAT. Trying to make sure I get my content review down. First off, very basic chemistry. Mass number on top, which means protons plus neutrons. Look at the periodic table. 12.01 is the mass of carbon, which would be the A, and the Z would be the proton number. The atomic number would be the Z. This is how they have formatted in the exam. Yeah, atomic weight is the weighted average. It's between different isotopes of let's just say carbon 6, carbon 12. I don't know if there's carbon 6, but carbon 12, carbon 14, and then they get the average of that, which would be 12.01. And there's several other isotopes of the same element. scientists contribute. I don't know if I have to memorize these people though. Rutherford just discovered that electrons exist on the nucleus, just electrons. But the Bohr model actually noted that there's orbits which these electrons travel through. The photon, the further the orbits from the nucleus, the more the energy. Atom structure. I have a Bing virus. It keeps switching to Bing. I need Google. Atom structure. This is very, very basic stuff. Energy states. Here, this is a close depiction of what I'm talking about. So these are the orbitals, but first energy is this one, second energy, third energy, fourth energy. As you're to be in every single energy level, you have to have a specific requirement, a specific amount of energy. I don't know if we need to go that deep in the details, but there needs to be more energy. I am assuming because you have to travel more distance around the nucleus. Anyways, photon emission. That's very simple too. Photon emission. Pretty much when an electron is excited, when there is energy, when the electron is excited, it jumps one state or two states. I don't even know, but it just jumps a state above its previous ground state to an excited state. And then when it starts losing energy and it goes back down, it releases some photons, which is pretty much light. See, photon is emitted, lower energy. When it jumps back to the lower energy, to its own ground state where it actually belongs. This is what it's saying here. Photon is emitted when energy state goes down. So it's emitting energy as it's jumping back down, closer to the nucleus. But it's absorbing this energy when it's jumping up an energy state, because you need more energy to be in the higher energy level. That's simple. I don't know what the hell this is, but this is a mnemonic. Absorb light, higher potential, excited, distant from nucleus. If you're excited, you're more distant from the nucleus, which from here to here, point A to B. B is farther away from nucleus than point A, and point B is where it's more excited. It's more energy. That part makes sense. Absorb light, higher potential. I don't know about that one. Heisenberg Uncertainty. It is impossible to know the momentum and position simultaneously. Basically means is when we observe, let's say this is the observer's view. Observer's view. When we're observing let's just say a ball rolling that way. Let's just say for this instant we stop and take a screenshot of it. We don't see any movement. That is the motion. That's the momentum. Velocity, momentum, same thing. We don't know the speed of it, but we know its position. That it's right here at, for example, point A. So Heisenberg Uncertainty says you can't observe both the momentum and the position at the same time, because momentum speed is when it goes from point A to point B, the distance between here to here. Then you find distance traveled over this time it took. So if this was time graph, and I don't know what the hell I drew up here, but you get the point. Who cares? Hund's rule. Hund's rule basically means electrons only double up in orbitals if all orbitals first have an electron. So, you know how we have these things right here? Filling up the orbitals. 1s, 2p, 1s, 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. I don't know if I'm doing something wrong, but let's just say 4p. Let's just say I'm doing this so wrong. There's this, there's that, there's that. We fill it up. We cannot fill up. Let's just, these are energy levels. And obviously this being below that, so like that. And basically, you fill it up. Let's just say you have one electron. It goes here. Second electron, we have to satisfy the Pauli's exclusion principle that says plus half and negative half, which means that these are the different orientations of the electron. One is up, one is down. So if there's 2 electrons, we go like that. If you have 3 electrons, up first that. And if you have 4, you have to do both. Now here comes the Hund's rule. You have 5 electrons here. Everything that we've done, simple. But when you have 6 electrons, you do not do this. Because the Hund's rule says all the orbitals first have to have 1 electron. This one has, these are called degenerate orbitals, which means that you have to fill it up before you do double it up, pair it up. So we do 1, 2, 3, 4, 5 electrons. Now let's say I have an element with 6 electrons. Up. Now let's just say we have 7. It's still up. Now we filled up all the boxes. Now let's say we have 8. Now we start filling it up. Down. Now this is the Pauli's exclusion principle. 9. 10, 11. I don't even know. 2, 4, 6, 8, 9. And then 10. And then we do this one. Why we don't fill this up before this? Because as you can see the boxes, it's in between these two, which means this is lower than that. These 3 boxes are lower than this right here. Okay, makes sense. Everything makes sense. The constants. Avogadro's number. 6.022 times 10 to the 23rd. It's such a simple thing. 6.022 times 10 to the 23rd. Simple. Let's write it again. 6.022 times 10 to the 23rd. Simple. Planck's constant, it gets more difficult. I don't know if I remember properly. 6.626 times 10 to the negative 34th. It's a negative because Planck's is the smallest unit of measurement. So 6.626. Okay, so they all start with 6. 6.26, no. 626 times 10 to the negative 34. I'm trying to use active recall. Okay, perfect. And speed of light is always easy. It's always 3 times 10 to the negative 8th. Eighth, not negative. Because speed of light is fast, not slow. And speed cannot be negative. That doesn't make any sense. Unless this is vectors. 10 to the 8th. That's simple. It's always 3. And it's kind of like easy to remember that a billion would be 10 to the 9th. A million is 10 to the 6th. But Planck's is right in between that. Well, not really between that, but right before that, so 10 to the 8th. I'm just thinking of like creative mnemonics to remember. And then this is where it gets interesting. Light energy. So nano, anything with nano in it is 10 to the negative 9th power, I think. Where is it? No definition. No, what the hell? Is it 10 to the negative 9th power? Found it. Micro is 10 to the 6th. Micro is 10 to the negative 6th. Nano is 10 to the negative 9th. Simple. Light energy. I'm glad I actually paid attention in class, because most of these are pretty simple. Light energy. Okay. We have two equations. We have this. Hc over lambda. It's called lambda. Then we have this. F being frequency, H being Planck's constant, C being the speed of light, and E standing for energy. Now, how do we derive, how does this make sense? How is this HF and how is this HC over lambda and it all gives us E? Well, one thing they're not saying here is that this is pretty much this. This is pretty much equal to this. This is pretty much equal to H times C over lambda. So technically now we can see like these looks very similar. So we can tell that H is there, and F is pretty much this then. So does F frequency equal to speed of light over wavelength? And it does. So we have three equations. But you only need to know this first one. When you know this one, you know every other one. Planck's constant 6.626 times 10 to the negative 34th. Speed of light 3 times 10 to the 8th. Avogadro's number 6.022 times 10 to the 23rd. Yeah. Okay, diamagnetic, and paramagnetic. Good, I paid attention to class. Diamagnetic are all electrons that are paired. So basically this thing right here. That and that. If it's paired. Think of it as complete. And if there's a magnetic field, which means just magnetic means the attraction between elements, because every element has magnetic abilities? I'm not sure, but this does not get attracted by anything. It just gets repelled because let's just think of this as a perfect scenario where it's a pair. Let's think of it as a couple. They don't want to be in another relationship with another pair. But let's just say we have one loner. This would want to be attracted to it. Let's just say this. Let's say this is moving away from it. Let's just say this is moving away from it, like get away from me. I don't know if arrow is a good depiction of it, but this, nah, that's not good. This is attracted, and this is repelled. Repelled and pulled, attracted into an external magnetic field. Anyways,
Why you're studying?
okay. Follow Hund's rule to build the atom's electron configuration. If one or more orbitals have just a single electron, the atom is paramagnetic. If there are no unpaired electrons, then the atom is diamagnetic. So diamagnetic, think of di as two, so there's two of them. Para, just one. Diamagnetic, repelled, because they're perfect. H, helium, 1s2, which is diamagnetic, and carbon is paramagnetic. That's where I got confused. And that's where I started searching up a video. Let's see. Where is it? Let's look at the
electron configuration for carbon. So we'll use the table on the right to get the correct electron configuration notation. So we'll go down first, the 1s, and s orbitals hold up to 2 electrons. So we'll put a 2 in there to show we have 2 electrons in that first energy level, that 1s2 there. Then we'll go down the next 2s, which also holds 2. We've used 4 of the electrons we have for carbon. So we go down the next row here and we have the 2p. And p's can hold up to 6, but we only need 2 more to use all the electrons for carbon. So we'll just put a 2 there. So the electron configuration for carbon, 1s2, 2s2, 2p2. If you add those numbers up, 2 plus 2 plus 2, you'll get 6. This is Dr. B with the electron configuration for carbon, and thanks for watching.
But how is that paramagnetic if there are 6 electrons? I don't understand. Paramagnetic and will be attracted to magnetic fields. Let's switch it up. It is carbon paramagnetic. My understanding that paramagnetic means that it is almost never found in nature in its atomic state, not two-state. Carbon always forms from unparalleled, so it is in contrast. Oh, so this one's saying it is diamagnetic. And here says it's paramagnetic. Did he make a mistake? Switch up a video. Paramagnetic and diamagnetic chemistry. Someone clearly made a mistake. Rather it's telling me it is diamagnetic, I'm saying it's diamagnetic. Here it says it's paramagnetic. Someone made a mistake here. Let's look at the most simplest one.
In this video, we're going to talk about how to determine if an element is paramagnetic or diamagnetic. So what you need to know is this. A paramagnetic element has unpaired electrons. A diamagnetic element does not have any unpaired electrons. So in order to determine this, we need to write the electron configuration for argon. The atomic number of argon is 18. So a neutral atom of argon has 18 protons and 18 electrons. Now, the S sublevel can hold up to 2 electrons. P can hold up to 6. D can hold up to 10. F can hold up to 14. We're going to write the configuration until the exponents add up to 18. So we're going to start with 1s. So we're going to have 1s2. And then after that, we're going to move on to 2s. So it's going to be 2s2. And then 2p and then 3s. So it's 2p6, 3s2. And then after that, 3p6. If you were to add the exponents, 2 plus 2 plus 6 plus 2 plus 6, you would get 18. So that is the electron configuration for argon. Now we're going to draw the orbital diagram for this element. So we have the 1s orbital, the 2s orbital, and then the 2p sublevel, and then the 3s sublevel, and then 3p. Now notice that each of these orbitals, they're completely filled with electrons.
It's called sublevel. Okay, in between it's called sublevel.
We have a total of 18 electrons in a neutral atom of argon. So we don't have any unpaired electrons in this example. Therefore, this substance is diamagnetic. A diamagnetic substance is one that is weakly repelled. So let's use aluminum configuration. Go to atom. Everything is going to be paired. P sublevel 1. We could say that aluminum is a paramagnetic substance. A paramagnetic substance is one that is weakly attracted to an external magnetic field. Now let's work on one more example. Let's try manganese. Feel free to try this example if you want. So you can write out the one part ratio. So this is the 4s3 level. So notice that we have 5 unpaired electrons in this example. Therefore, manganese is highly paramagnetic.
Okay, so I was right. Carbon should be diamagnetic because there's 6. The atomic number is 6. Where is carbon? You get the point. You get the point. 6. So carbon should be diamagnetic because there's 2 of them. And helium has, I hate the Bing virus. Helium atomic number. It is 2. Which is also diamagnetic. Someone made a mistake here. But one thing interesting he said here, where is it? Where did the video go? Bruh. Okay, one thing he said that was interesting was that he drew something like that. The sub. He said it was 4 up. He said because there's 4 unpaired electrons, this is highly attractive element. But if there's just one, it's weak attraction. I think it would be the same thing if it was like this, I guess. Does it go the other way? It's highly repelled. I don't know. Highly repelled. Anyways, let's skip this. I mean, I'm not really skipping, but I feel like I'm still like gray in this area, so I'll do some research on that. Quantum numbers. Bullshit. This is basically memorization. Quantum number. N is the principal, but it labels energy level or shell number. Electron energy level or shell number. Possible values 1, 2, or 3. Except for D. Search up. I'm kind of gray in that area right now. Quantum numbers.
Professor Dave here. Let's learn about quantum numbers.
He knows a lot about the science stuff. Professor Dave explains.
Now that we understand that electrons are both particles and waves, we are ready to learn about how electrons are arranged in an atom.
Okay.
The location and energy of every electron in an atom is determined by a set of 4 quantum numbers that describe different atomic orbitals. An orbital is a region of probability where an electron can be found. There are s, d, p, and f orbitals with different shapes, and they look like this. Remember, these shapes are not electrons, just regions in space where electrons can be, and each one can hold up to 2 electrons. The more electrons an atom has, the more of these orbitals it will need to accommodate them all. The first quantum number is the principal quantum number n, which can have any positive integer value. We saw this when we learned about the Bohr model. It represents the energy level of the electron. Each learned about the Bohr model,
principal?
which can have any positive integer
Principal
value.
quantum number.
We saw this when we learned about the Bohr model. It represents the energy level of the electron. Each orbital will have an n value, and the larger the value of n, the further away from the nucleus it is. The next quantum number is the angular momentum quantum number, L. This can have any
Oh, it's n minus 1.
value from 0 to n minus 1. For example, if an electron has an n value of 3, it can have an L value of either 0, 1, or 2.
Oh, you have to count from 0 up to n minus 1.
Because 2 is 3 minus 1. The L value describes the shape of the orbital.
It would be the
When L
opposite
equals
thing.
0, we are describing s orbitals, which are spherical.
It's the opposite?
Just one of these per energy level. When L equals 1, we are describing p orbitals, which are lobes that extend outwards on 3 axes. There are 3 of these per energy level. When L equals 2, we are describing d orbitals, which are weird looking, 5 of these per energy level. And when L equals 3, we get f orbitals, which are even weirder looking, 7 per energy level. Next, we have the magnetic quantum number m sub L. This can have a value of anywhere from negative L to L. So if L is 2, m sub L can be negative 2, negative 1, 0, 1.
Fuck. How did he get L?
Zero, 1, or 2, because 2 is 3 minus 0. L equals describing s orbitals, which are spherical, just orbital. When L equals 0, we are describing s orbitals, which describes the shape 2, because 2 is 3 minus 1. The L value describes, which are p or per energy, 5 of these 7 have a value of anywhere from negative L to L. So if or 2. This quantum number determines how many orbitals there are of a type per energy level, and therefore describes a specific orbital amongst a particular set. When L is 0, m sub L must also be 0, and that's why there's only one s orbital per energy level. When L is 1, m sub L can have 3 values, which is why there are 3 p orbitals per energy level. An L value of 2 gives us 5 values for m sub L and 5 d orbitals, and an L value of 3 gives us the 7 f orbitals. The last quantum number is an easy one. It's the spin quantum number, m sub s. This one will be either 1/2 or -1/2, no matter what. So every electron in an atom has a unique set of quantum numbers. No two electrons in an atom can have precisely the same 4 quantum numbers, as is stated by the Pauli exclusion principle. This is because any orbital can only hold up to 2 electrons, and even the 2 electrons in the same exact orbital will have opposite spin values. So let's try to describe different sets of quantum numbers and what they mean. When n equals 1, L must be 0, and m sub L must also be 0.
Okay.
That means we are describing the 1s orbital. It can accommodate
My question is, do I have to write this whole thing out?
2 electrons, which will have spins of 1/2 and -1/2 respectively. This is the lowest energy orbital, so any atom on the periodic table will fill this orbital first. The electrons in hydrogen and helium occupy this orbital since they have only 1 and 2 electrons respectively. When n equals 2, L could be 0.
Wait, so
which
what
2
is
electrons
the ms? It's plus 1/2. Wait, why?
of 1/2 and -1/2 respectively. This is the lowest energy orbital, so any atom on the periodic table will fill this orbital first. The electrons in hydrogen and helium occupy this orbital since they have only 1 and 2 electrons respectively. When n equals 2, L could be 0, which would give us the 2s orbital, or L could be 1, meaning m sub L could be -1, 0, or 1,
You do have to write
giving
them
us
out.
the 2p orbitals. The outermost electrons in the second row of the periodic table will occupy these orbitals. When n equals 3, L could be 0, giving us
1.
the 3s orbital. L could be 1, giving us the 3p
Maybe
orbitals,
2,
or
this
L
is 3
could be
minus
2,
1, 2.
giving us the 3d orbitals.
And that would be 0, ml would be 0. ml would be -1, 0, 1. -2, -1, 0, 1, 2.
A large atom will have to use all of these orbitals and more to house all of its electrons. The Aufbau principle tells us the order in which an atom will fill up its orbitals. This is determined by their relative energies. Orbitals that are further away from the nucleus have higher potential energy, so it'll be 1s first, then 2s, then 2p, 3s, 3p, and so forth. We can use this to determine the electron configuration of any atom. For example, a neutral chlorine atom has 17 electrons. So looking at the orbitals, each of which can hold 2 electrons, let's fill them up starting at the lowest energy and then climb upwards. The 1s orbital gets 2 electrons, one spin up, the other spin down. Then the 2s, then the 2p's, then the 3s, and the last 5 will go in these 3p orbitals. Hund's rule says that for electrons of the same energy, you put 1 electron in each orbital first before doubling them up. So 1, 2, 3, 4, and 5 gives us a total of 17 electrons for chlorine. That means chlorine has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. The numbers before the letters are the n value for the orbital. The numbers after the letters tell you how many electrons sit in each type of orbital. If you want a quicker way to determine electron configurations, just know which areas of the periodic table correspond to which types of orbitals. This area is called the s block. This is the p block, here's the d block, and then the f block. When we are determining the electron configuration for an atom of a given element, the easiest way to do it is just travel left to right and up to down on the table until you get to the element, since each element has 1 more electron than the last. Looking at chlorine again, the top row is just the 1s orbital, that's full, so 1s2. Going to the second row, where n equals 2, we fill the 2s orbital, which holds 2 electrons, hence 2 elements, the 2p orbitals, which hold 6, so we pass 6 elements. Then the next row down, we fill the 3s orbital, and lastly, we get to the 3p's and count 1, 2, 3, 4, 5, 3p5. A common abbreviation is to use the noble gas from the row above and list it in brackets. This would be read as neon,
and then 3s2, And then 3p, 1, 2, 3, 4, 5.
And it implies the ground state electron configuration of neon. Then you just list the valence electrons of the element, or the
3s2,
ones that correspond
3p5.
to the row it is in.
So you're supposed to use
We
a
can
noble
use
gas.
orbital diagrams to visually depict.
This is useful because if you have to do something like, what is this even called? Indium. Instead of writing every one of these electron configurations, you can just skip it and then go to the noble gas krypton, and then work from there.
That correspond to the row it is in.
All right, this is supplementary. I don't need it. So just to refresh it in my mind, the n, which would be given to you, because how would you know? They would tell you which one they're talking about. It could be 1, 2, 3, and it could keep going till how much ever orbital. So let's say n was 3. That means L has to be. Why did I write the L like that? But I think that's how he wrote it. L is it has to be 0. It could go up to 2 because it's n minus 1. Then it's 1, 0. You have to always have a 0. And then ML would be for each of these. 0 would be 0 for 0 for ML of 0. I don't know if that's how it works. ML of 1 would be -1, 0, and 1. So it only goes up to 1 or -1, the opposite of it. ML of 2 would be -2, -1, 0, 1, 2. And then the other one, the spin, I don't even know. It's always this? I think it's always this. I don't know. Next. Maximum electrons in terms of n, 2n2. Maximum electrons in subshell, 4l plus 2. I don't get that. What is it trying to say? Maximum electrons in terms of n is 2n2. Maximum electrons. Whatever. Free radical. An atom or molecule with an unpaired electron. Oh yeah, we learned about it in biology. Radicals are like dangerous because at the electron transport chain, where the electron of hydrogen is used, let's just say the E negative is moving throughout the lipid bilayer, and it goes on. And there's little 5 complexes, ATP8 synthase or something like that. I don't know, there's like 5 complexes. As it's traveling the electron, the oxygen, I think, picks it up, the extra electron, and then it has an unpaired electron. That makes the oxygen a radical. So you need antioxidants. It's to stay healthy, because it can cause cancer. This is not chemistry. This is like biochemistry. Okay, everything makes sense. Atomic orbitals on the periodic table. 1s. It gets more complicated down here. You see right here? You see how 1, 2, 3, 4, 5, right? Then you might be like, why is this 3 and this is 4? 1, 2, 3, 4, 5, right? Why is this 3? Well, there's a rule you have to memorize. I forgot what it was, but this is going to be 3. Because this would fill. This is a subshell. This would fill in before that. So 3D, 4D. You have to memorize that. It's gonna be 1 less than that. So 3, 4, 5, and it would keep going. 2, 3, 4, 5, 6. Everything's similar here. Yep. 4F, 5F. I don't understand this one. Whatever. It rarely goes up to this. 3D shapes of SPDF orbitals. Who cares? Anywho, the off-bow principle, which says direction goes down, which you can do yourself, 1s, if you have a periodic table. But I think this, something that I just noticed now, after so many years of chemistry, is that it's 1, 2, 3, 4, 5. Let's just say 5. S would be here, and then it just keeps adding SP. It's because it's SPDF. SPD, right? SPDF, and then so on and so forth. I don't know if it repeats and it becomes F1, F2. Get off. Well, principle. So it's pretty much S, P, D, F. This is the first time the F on the 4th energy level. And then on the 5th one, you add 5F. You don't add another F. It just becomes a 5F because it's a 5th level. But this is 4, this is 5, okay? And then you just stop using the Fs in general, at all. Then it becomes SPD, SP, S. You just make a triangle. But here somewhere is a rule why this is supposed to be 3D. Where do we see the 3D? 1, 2, P, 3D. Look. 4S. 4S. And then look at the line. It goes straight to 3D. And then 4P. That's why it's 3D. Because you're filling it up. You see how this is still on the 3rd line? You're going through 4S, and then you're going back to 3D. This line right here. And then you're going back to 4P, the 4th level. 3rd level, 4th level. So you just have to follow the line. If you remember the structure, I think you'd be able to write any electron configuration easily. Okay. Simple. Alkali metals down here. Alkaline earth metals, transition metals, post-transition metals, metalloids, nonmetals, halogens, noble gases, and some rare earth metals. That's why helium is on the right side, not here, because helium is noble gas. That's why it's, even though it's the S's, you use it here somewhere. See how he has the helium and the hydrogen together? The helium and hydrogen together. But in reality, it's actually two different, so they separate them too. Metalloids. Okay, I'm just trying to figure out a nice shape, like how can I do it? So we know the two are filled up here, noble gas, halogens. And then this is what you only have left to work with to separate them into 3. So this looks like a freaking stealth bomber. And this also looks like a stealth bomber plus the one up here. And then everything else would be metalloids. So stealth bomber. If I could draw it, I would do it. Hold on. Forget about these. Forget about this. This looks like a stealth bomber. That's what a stealth bomber looks like. These are, by the way, being replaced by B-21. So RIP, no, Raptor, RIP, B-21, B-21. Raider. These are the new 2021 models of it. Anywho, want to steer it a little off topic. Stealth bomber here again, but you are adding one more, so one wing is longer, and then everything else is this. Anywho, that's just an easy way of remembering it. Okay, next. Do I have to remember the names? Alkaline earth metals, rare earth metals, metalloids, non-metals. Pull between nucleus and valence electrons, unchanged. What is this? I've never seen this before. What is this? Oh, you use this table. It's okay. Pull between nucleus and valence electrons. CF. Ionization energy increases. Oh, you lose electrons. Hold on. What? I hate how T didn't actually explain it. Double gas have no affinity for electrons. It would take energy to force on E on them. It would take energy to force it. Gain electrons. The delta H meaning fuck. What was delta H? 0 when gaining electrons is less than 0 when gaining electrons. But EA is reported as positive value. What the fuck is this? CF chemistry. Oh. I've never learned this before.
Let's talk about effective nuclear charge.
Effective
How can we
nuclear
calculate that
charge.
for an electron in an atom? Well, let's talk about effective nuclear charge. Well, let's start with this problem. What is the effective nuclear charge for an electron in the n = 2 shell, let's say in an atom of fluorine? Well, the first thing we're going to do is draw a picture. Now, hopefully you have a periodic table with you. You want to determine the atomic number of fluorine. The atomic number of fluorine is 9. So this tells us that fluorine has 9 protons in its nucleus.
Come on, get to it, champ. Come on. I don't have much
In
time.
the first energy level, there are 2 electrons. These are
Okay.
known as core electrons.
Thank you.
And in the second energy level,
You have
of
8 up to
fluorine,
8
there's 7.
because there's 7 left over.
Keep in mind, atoms have equal number of protons and electrons.
Okay.
So the number of protons in fluorine is 9, represented by the symbol Z. So an atom, which is electrically neutral, will have 9 protons and 9 electrons. The first shell can hold 2 electrons, so the second shell has to have 7, because 2 plus 7 is 9. So now, our goal is to find the effective nuclear charge of one of these electrons. By the way, the electrons in the outermost energy level, what are they called? These electrons are known as valence electrons. To calculate the effective nuclear charge, this is the simplified way. It's equal to the number of
Okay, based on everything that I think I got it. The pull between nucleus and valence electrons. The nucleus of the atom and the valence electrons orbiting around it. So, as you're going from left to right, the atomic number is increasing, so there's more electrons. So 3, 4, 5, 6, 7, 8, 9, 10. Now, the more electrons and the further away they are, the more the nucleus has to pull on it to make sure it doesn't lose it. So it has to pull harder. So the effective nuclear charge, so it's called effective nuclear charge, which is ZF, effective nuclear charge, would increase as you're going from left to right. But it says it's unchanged as you're going up or down, up and down, or down to up. It doesn't really matter, because based on my understanding, that this is the S, then this is the P's, the D's, and the SPD, and then F. SPDF means different orbitals that these electrons are filling in. So if we went from chromium to rubidium, it wouldn't matter. Why wouldn't it matter? Why wouldn't it matter? Hold on. It wouldn't matter because rubidium is filling up a whole different orbital. So wouldn't I want to make sure it's closer? I'm confused.
Of protons in the nucleus, Z, minus the number of inner shell electrons, or core electrons. So there's 9 protons in the nucleus, that's the atomic number, and there's only 2 inner shell electrons with respect to this one. So those 2 electrons that I've just highlighted here, they shield this electron from the nucleus, thus reducing the effective nuclear charge.
What?
Electrons, inner shell electrons, and there's only 2 inner shell electrons with respect to this one.
Yeah.
So those 2 electrons that I've just highlighted here, they shield this electron from the nucleus, thus reducing the effective nuclear charge. So it's 9 minus 2, which is 7. So that is the effective nuclear charge on an N equal 2 electron. Now, the N equal 1 electron, their effective nuclear charge is about 9, because there's no other electrons between this electron and the nucleus.
So why does that say increasing
So
them?
they feel the greatest nuclear charge because they're so close to the nucleus.
If we're talking about the first 2 elements,
Now let's move on
the
to our
electrons would
second
be on
example.
the smaller end of
What
the
is the
elements.
effective nuclear charge for an electron in the N equal 3 shell in an atom of aluminum? Now, if you want to try this problem, feel free. Go
Yeah, I
ahead and
got it, but I'm not understanding. Do I just memorize this? Aluminum. Aluminum. Atomic number 13. 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 or 14? 13. 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So, I think if we're following the same principle, 1, 2, 3, 13 minus 1, 2, 3, 4, 5, 6, 7, 8 minus 1, 2. Is that how it works? Am I? Yeah, I'm confused.
pause the video and a similar number of to the periodic table, you'll see 13 above aluminum and 26.98 below it. 26.98 is the mass number. Always going to be maximum total, but are different. So now let's put the last 3 electrons in the outermost energy level. 10 minus S. So how many inner shell electrons do we have? We have 2 in the first shell, 8 in the second shell. So we have a total of 10 electrons that exist between the nucleus and this one.
This one doesn't count. 2, 3, 4, 5, 6, 7, 8, and then 2. Oh, did it right? What?
So there's 10 inner shell electrons.
Yeah, 8 minus. So mine's just. You just simplified more. So 13 minus 10. 3. So we don't. This doesn't affect it. So these are shielding it. Shielding. He just says shielding it to make it easier for us to understand. But what's really happening is, it's farther away from aluminum, so it's hard. Aluminum has a harder time pulling it. So it's a less effective nuclear charge.
So it's going to be 13 minus 10, which is 3.
Okay.
So that is the effective nuclear
What?
charge for an outermost electron in aluminum in the N = 3 shell. Now let's work on one more example for the sake of practice.
This fucking stupid shit's so annoying.
What is the effective nuclear charge, let's say for an electron in an atom of chlorine in the third shell?
Candace. Nice.
So let's begin with the formula. Now, what is the atomic number of chlorine? Chlorine has an atomic number of 17. And so there's 17 protons in its nucleus.
Yeah.
The first shell has 2 electrons.
17. 2. Then it's 8.
Now the third shell, the last shell, has the remaining 7 electrons. So those are the 7 valence electrons in chlorine.
It would still be the same.
So now let's finish this problem. So we have an atomic number of 17, and for an N = 3 electron, we see that there's 10 in.
Okay, so it makes sense that it's unchanged, because first level, second level, third level, fourth level. Wait, what? Is that how it works?
Inner shell electrons. 2 in the first, 8 in the second. So the effective nuclear charge is +7.
It does change.
And notice that this is equal to the number of valence electrons in a chlorine atom. When dealing with representative elements in, let's say, groups 1, 2, or 3 to 8, if you're looking for the effective nuclear charge of a valence electron, it's the same as the group number. And so that's it for this video. If you like it, feel free to subscribe to this channel. And if you're going to do this, don't forget to click on that notification bell. Thanks for watching.
Okay, so now we know how to calculate this. I want to know why it's unchanged. Let's search up Reddit. Why is... Oh, let's search up here. Why is ZF unchanged as you go down a column or row? Row. Column. Fuck, which one is column? Which one is row? Column, row. Fuck, this is so stupid. Column. So row, this is column. So row, yeah, that's right. Or row. Chlorine has a large electron affinity than fluorine. What? More protons in the nucleus cause stronger charge to electron at the same energy level. Oh, that makes sense from going left to right, yeah. I don't know why it doesn't do that for when it goes down. No. Whatever. That makes sense. You can look all your answers in Brainly. Brainly? Brainly. This looks like I have to pay for it. This is homework help though. You post a question and they answer it for you. Like check. This is not what I want though. I'm just trying to study why. You don't? How long would it take though for them to answer my question? Because I need to know this like right away so that I can move on, or else I feel like I'm not able to move on. I hate when I don't know something. It pisses me off. Yeah. I know like freaking half of all this shit, which is not good. So far so good, but like, why am I stuck on this? I've never heard of this. I literally, you copy paste the question and it will give you the answer. Yeah, but the problem with that is it's... Yok man, but the problem is, it's not a question, like a homework question. This is like my own question. How do I join for free? I'll save this for now. I bookmarked it. I bookmarked, done. I'll look into it later. Okay, let's move on. Ionization energy increases as you go from left to right. Ionization energy. What the fuck was ionization energy? Ionization energy was... If I remember, I'm not looking. Ionization energy is... Ionization energy is... I know this, bro. This is such an easy ass question. Ionization energy. Fuck, I forgot. Isn't there a chart for this then? Chart. There's an ionization. No, there isn't. Wait. Is the minimum amount of energy required to move the most loosely bound electron of an isolated neutral gaseous atom or molecule? It's good to know. Let's get a refresher. I don't want to delve too much into it. So knowing basic stuff, because this is just content review. This is just understanding. So when I'm actually studying for the test, I won't be you know, confused, in shock. Like, what is that? 32 minutes? Are you joking?
So let's talk a little bit about a word you might have heard, and that is ion. Let's talk about what it is, and then we'll talk about trends in the periodic table on I guess, neutrons are obviously also protons, does not equal the number of electrons. And you can have positive ions if the protons are more than the number of electrons. Protons are positive, electrons are negative. And you can have negative ions if the number of electrons are greater than the number of protons. For example, if you just had hydrogen in its neutral state has 1 proton and 1 electron. But if you were to take one of those electrons away, then hydrogen would have a positive charge, and essentially it would just be, in its most common isotope, it would just be a proton by itself.
This is why I hate watching Khan Academy. It tells you the most useless, the most obvious things. Like, we know this. You don't have to tell me this.
And electrons and cations. Likewise, so fluorine gains an electron. It's going to have a net negative charge.
Anion, yes.
All this to
Yeah.
energy required.
That's what I need.
Energy required
To
remove an
the
electron.
electron.
To remove an
But we're talking about
electron.
atoms here, so would it be the valence
So it could have
electrons?
even been called cationization energy, because it's the energy required to remove an electron and make the overall atom more positive. So let's think about the trends, and we already have a little bit of background on the different groups of the periodic table. So for example, if we were to focus on, especially, we could look at group 1. And we've already talked about hydrogen's a bit of a special case in group 1, but if we look at everything below hydrogen, if we look at the alkali metals here, we've already talked about the fact that these are very willing to lose an electron. Why? Because if they lose an electron, they get to the electron configuration of the noble gas before it. So if lithium loses an electron, then it has an outer shell electron configuration of helium. It has 2 outer electrons. And that's kind of, we typically talk about the octet rule, but if we're talking about characters like lithium or helium, they're happy with 2, because you can only put 2 electrons in that first shell. But all the rest of them, sodium, potassium, etc., if you take an electron away from them, then their outermost shell, well, all of them, their outermost shell, they're going to have the electron configuration of the noble gas before it. And for sodium on down, that outer shell is going to have that perfect 8. Lithium, if you remove an electron, it would get to helium. It will have 2 electrons in its outer shell. So you could imagine that the ionization energy right over here, the energy to require, the energy required to remove.
Oh, it's the reactivity of an element, how much it's, like, if it has an extra valence electron, how much it wants it to be removed. Like metals, they have valence electrons, they want to be perfect like noble gases. So they want to give up that electron. Okay, that makes sense.
Electrons from your alkali metals is very low. So let me just write down. This is, so when I say
Okay, I got the conceptual part of it, but I just want to know the math part.
low,
Where's the
I'm
math
talking
part?
about
How do I
low
use this in math?
ionization table. In fact, let's go all the way to the right on the about. They're very, very, so it would be charge Well, within
Do I calculate it or is it
any
given to
group,
me? I
if
think it's
we
given to
look
me.
at the alkali, if we look at the alkali metals right over here, if we're down at the
So the trend says it's going up. Going up means there's higher ionization energy because why?
bottom, if we're looking at say cesium right over here, that electron in the 1, 2, 3, 4, 5, 6 in the sixth shell, that's going to be further from that one electron that lithium has in its second shell. So it's going to be further away. It's not going to be as closely bound to the nucleus, I guess you could say. So this is going to be even that one electron is going to be even easier to remove than the one electron in the outermost shell of lithium. So this one has even lower.
Hold on, ionization energy means the energy required. Oh, I'm dumb. I'm right. The noble gases are perfect. They have the full octet, 2, 8, 8. But these ones don't. So as you're going towards the noble gases, the amount of energy required to remove the valence electron is increasing. So you need to input more energy to get rid of those extra valence electrons. But these ones here only have one extra electron, or so I'm assuming one extra valence electron. These have like 6 or 7, 5, 6, 7, 8. Is that how it works? 5, 6, 7. Yeah, I think that's how it works. Valence electrons. These have 1. So as you're going towards it, the ionization energy increasing. So you need more energy now to remove that electron because there's more valence electrons. Here is less, but it's decreasing when you go down because the atomic size is increasing as you're going down, which means that the atom is much bigger now, and this one puny little electron so far away from the nucleus is so easily, you can easily steal it from this element because it's so far away that it's not prioritized because it's so far away. So ionization energy is increasing as you're going up because the atomic radius is getting smaller. And as you're going to the right, you're going close to the noble gas, which means there's more valence electrons to be removed because there's more valence electrons at the outer shell. Okay, makes sense.
Lower, even lower. And that's even going to be true of the noble gases out here. That xenon, that
Where's the math? Where's the math?
Charts like this because it kind of shows.
They don't tell you. You just have to know the strength. Okay. EA Sports. Noble gases have no affinity for electron. It would take energy to force induction on them. Isn't this electronegativity is here. What is EA? Yeah, what's going on? Search up Bank Bros. That's another web to help with your homework. Bank Bros. Yo, let's go. Firm. FNM. Fortnite. We need you, Sova. I swear to God, Bang. I feel like I'm getting caught here. Bang Bros. No, hold on. You're trying to catch me. You're trying to catch me. I'm not stupid. Bang Bros, come on. Come on. Bang Bros. Yeah, I'm sure it helps. I can't believe you actually said that. Nah, shut up. I'm not playing Valorant right now. I'm studying. Do you know who I am? Alright, I'm gonna not show it. You're gonna see my reaction to it. Okay. I swear to God, I feel you're catching me. Bang Bros. Bangbros.com. Thank you. Thank you. What I say? It was calling me. I was like bang bros, bro. I'm so into studying right now that something like that could like easily get by me. Like it would easily, yeah, yeah, help me a lot. Easily. So what is EA? I want to know what EA is. I hate how it doesn't say it. EA chemistry trend. Electronegativity. I already know that. Electron affinity. I feel dumb. How did I never learn this? 13 minutes? Fuck it. Switch game. Oh, AMC.
Before we get into electron affinity, let's really quickly review ionization energy. And let's start with a neutral lithium atom.
Oh god, I need to pee. God damn it, hold on. How did you know Bangalore is useless? Me? I have surface level knowledge about everything. Never watched it though. No, my friend told me about it. Said, "Yo, don't get caught by it," and I didn't get caught. Thank God he told me about it. 1 second, I'll be back.
When are we going to Wilbur's wedding? August. Are we gonna miss Sabrina's birthday? The 9th? The week. What is the day for a week?
Razors, yeah. Okay, so the thing is, right? As you're going more into chemistry, it gets more difficult. But that's where people think, that's where the misconception comes. They think, oh, because it gets harder, it gets boring. I think it's the former. I think it gets actually interesting. I think it's the latter. It gets more interesting because you have basic level knowledge about chemistry. That's where the problem is. People don't have the basic level knowledge about it, so they can't learn the advanced stuff. So it's less interesting because they struggle more with it. But if you know all of this, once you have the basics down, everything else becomes so much more interesting.
With an electron configuration of 1s2, 2s1. A lithium atom has 3 protons in the nucleus, so a positive 3 charge, 2 electrons in the 1s orbital, so here are the 2 electrons in the 1s orbital, or our core electrons, and 1 electron in a 2s orbital. This is our outermost electron, our valence electron. The valence electron is shielded from the full positive 3 charge of the nucleus by the presence of the core electrons. So like charges repel, and these core electrons repel this outer electron and shield it from the full positive 3 charge. But there still is an attractive force between the positively charged nucleus and this outermost electron. So opposite charges attract, and our outermost electron still feels a pull from the nucleus. Therefore, since the outer electron is attracted to the nucleus, it takes energy to completely pull away this valence electron from the neutral atom. So if we pull away that outermost electron, we lose our valence electron and we're left with a lithium ion with a positive charge. Positive 1 charge because we still have 3 protons, but only 2 electrons now, so overall a +1 charge. Since this ionization takes energy to rip away the electron, the ionization energy is positive and it's measured in kilojoules per mole. Let's compare that with electron affinity. So in electron affinity, let's say we're starting with our neutral lithium atom again, but this time, instead of taking an electron away, we are adding an electron. So we would add an electron to the 2s orbital. So we started off with 3 electrons in the neutral lithium atom, and we're adding 1 more. So the electron configuration for the lithium ion would be 1s2, 2s2. So still 3 positive charges in the nucleus, 2 electrons in the 1s orbital. But now we've added an electron, so we have 4 electrons total, 2 in the 2s orbital. So let me highlight the electron that we added in magenta. So this is the electron that we added to a neutral lithium atom. And this electron, we know, is shielded from the full positive 3 charge of the nucleus by our 2 core electrons in here, right? So like charges repel. It's also going to be repelled a little bit by this electron that's also in the 2s orbital. So this electron is going to repel this one as well. But there is an attractive force between our positively charged nucleus and our negative charge on the electron. So this electron that we added still feels an attractive force that's pulling on it from the nucleus. And so if you add this 4th electron, energy is given off. And since energy is given off, this is going to have a negative value for the electron affinity. For adding an electron to a neutral lithium atom, it turns out to be -60 kilojoules per mole. So energy is released when an electron is added. And that is because the electron that we added is still able to be attracted to the charged nucleus. So if the nucleus has an attraction for the added electron, you're going to get a negative value for the electron affinity. Or that's one way.
That's a shitty video. I understood absolutely nothing about it. It's the amount of energy required to detach 1 electron from a negatively charged ion. It is indicated using simple EA and usually expressed as filters. Electron affinity is the amount of energy required to detach amount of energy. Oh, I'm dozing off. Amount of energy required to detach 1 electron from a negatively charged ion. Negatively charged means there's an extra electron that it needs to be. It's something that needs to click. Hold on. Okay, let's get this one. I'm so confused. What the hell is this? Electronegativity is simple. That's interesting. Chromium and xenium or whatever has. Why does chromium have electronegativity? It doesn't tell me. Yeah, we already know electronegativity. So electronegativity increases as you're going up and right because okay, let's just start from the first one, left to right. Why is it increasing? Because electronegativity means. Why am I so gray in this area? I feel like I did so much advanced stuff that I just forgot all the basic stuff, which is not good. Chromium definition. Electronegativity definition. Electronegativity is a tendency of an atom to attract shared electrons to itself.
Electronegativity, symbol Chi, of both its atomic number and the distance at which its valence electrons reside from the charged nucleus. The higher the associated electronegativity number, the more an atom or a substituent group attracts electrons towards itself. On the most basic level, electronegativity is determined by factors like the nuclear charge and the number, location of other electrons present in the atomic shells. The opposite of electronegativity is electropositivity, a measure of an element's ability to donate electrons. The term electronegativity was introduced by Jöns Jacob Berzelius in 1811, though the concept was known even before that and was studied by many chemists including Avogadro. In spite of its long history, an accurate scale of electronegativity
What I want to it's when that atom is part of a covalent bond, when it is sharing electrons with another atom. So how much they want electrons. And you can see that these are very related notions. This is within the context of a covalent bond, how much electron affinity is there. Well, this you could think of it as
That's
a slightly
confusing me
broader
because I don't know
notion, but these two trends
why are they different?
go absolutely in line with each other.
Because they do, yeah.
And to just think about electronegativity, make it a little bit more tangible, let's think about one of the most famous sets of covalent bonds, and that's what you see in a water molecule. Water, as you probably know, is H2O. You have an oxygen atom, and you have two hydrogens. Each of the hydrogens have one valence electron, and the oxygen has, we see here in its outermost shell, it has 1, 2, 3, 4, 5, 6 valence electrons. 1, 2, 3, 4, 5, 6 valence electrons. And so you could imagine hydrogen would be happy if it was able to somehow pretend like it had another electron. Then it would have an electron configuration, a stable first shell that only requires 2 electrons. The rest of them require 8. Hydrogen would feel, hey, I'm stable like helium if it could get another electron. And oxygen would feel, hey, I'm stable like neon if I could get 2 more electrons. And so what happens is they share each other's electrons. This electron could be shared in conjunction with this.
You see the freaking numbers, please.
Oxygen, electron, negative electron, covalent bond, these reports become charges on properties, and also or a lot of the likely molecule is through a period. What do you and for that? So the gaseous state way. Well, I'll give you a hint. Think about atomic radiation. Getting more protons. Through as we go through a period. Let's say as we start in group 1 and we go to group, and as we go all the way to
electronegative. It wants to be more negative, means it wants more electrons. Oxygen is closer to being a noble gas than the hydrogen is. Well, no, never mind. That's not a good example. Na is closer. Chromium, sulfur is close to being. Well, it's not going to become aluminum, but to get a full octet, it's closer to it than the Na because it has 1 valence electron.
Let's say the halogens all the way up to.
And if it's increasing, electron is increasing as you're going up because
The yellow column right over here what do you think is going to be the trend for electronegativity? And once again, one way to think about it is think about the extremes. Think about sodium and think about chlorine. And I encourage you to pause the video and think about that. Or it's a similar idea as ionization energy. Something like sodium has only one electron in its outermost shell. It would be hard for it to complete that shell. And so to get to a stable state, it's much easier for it to give away that one electron that it has so it can get to a stable configuration like neon. So this one really wants to give away an electron. And we saw in the video on ionization energy, that's why this has a low ionization energy. It doesn't take much energy in a gaseous state to remove an electron from sodium. But chlorine is the opposite. It's only one away from completing its shell. The last thing it wants to do is give away an electron. It wants an electron really, 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 really badly. So it wants to do is give sodium. But chlorine is the opposite.
The minimum amount of energy is decreasing. Since it's all the way on the left, it's less ionization energy. That means the minimum energy. So the minimum energy required to remove it is so little that they could just pretty much give it away for free. Not really. Just using it to exaggerate it to make sense more.
Opposite. It's only one away from completing its shell. The last thing it wants to do is give away an electron. It wants an electron really, 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 really badly so it can get to a configuration of argon, so it can complete its third shell. So the logic here is that sodium wouldn't mind giving away an electron, while chlorine really would love.
So ionization energy is to give up its electron, and electronegativity is to attract electrons.
An electron. So chlorine is more likely to hog electrons, while sodium is very unlikely to hog electrons. So this trend right here, when you go from the left to the right, your electronegativity, let me write this, you're getting more electronegative. More electronegative as you go to the right. Now, what do you think the trend is going to be as you go down, in a group? What do you think the trend is going to be as you go down? Well, I'll give you a hint. Think about atomic.
Ionization energy is the amount of energy required to remove an electron.
Radii. And given that, pause the video and think about what do you think the trend is? Are we going to get more or less electronegative as we move down? Everything here, all the group 1 elements have one electron in its outermost shell, but that 55th electron, that one electron in the outermost shell in cesium is a lot further away than the outermost electron in lithium or in hydrogen. And so because of that, it's
easier to get rid
there's
of
more
it.
interference between that electron and the nucleus from all the electrons in between them, and also it's just further away, so it's easier to kind of grab it off. So cesium.
Okay, and they all have like up, right, except the atomic size. I never knew this rule here. Cations less cations, neutral anions. An anion will have more electrons, which means it would be bigger. Right? Does that make any sense? Anions would be greater than neutral, and neutral would be greater than cations. Because anions have more electrons, which would mean increasing the atomic size. That makes sense. So I kind of knew this subconsciously. Covalent bonds, we're getting to the juicy part. Let's see. Covalent bonds. Formed via the sharing of electrons between two elements of similar electronegativity. Covalent bonds means actual sharing it. Polar ionic bonds would be like slightly positive, slightly negative. Like oxygen and hydrogen. Sigma positive, sigma negative. Because this is hogging at this higher electronegativity. Electronegativity is... What the hell did I just draw? Electronegativity is higher here than here for this element. Bond order reverse whether a covalent bond is single, double, or triple bond. As bond order increases, bond strength, bond energy. As bond order increases, bond strength, bond energy, bond length. Never heard of bond length before. This is the electronegativity. Between 0.5 down, less than 0.5, not 0.5 included, I think. Let me see. Electronegativity chart. Images. Rule. If the electronegativity difference, usually called EN, is less than 0.0, then the bond is non-polar covalent. If the EN is between 0.5 and 0.6. So less than, not included. And then if it is between 0.5 and 1.6, the bond is considered polar. But if it's greater than 2, then the bond is ionic. What happens if it's in between that? I guess it would still be polar covalent. Oh, what about the gap between what's so the rule number 4 is it's in between what's if a metal is but then the bond is considered ionic. Polar covalent. Not only non-metals are involved, it's considered polar covalent. Polar. What does polar mean again? Polar bond. Definition. It's a type of covalent bond between two atoms in which polar and non-polar. It's a type of covalent bond between two atoms in which electrons are shared unequally. The type of covalent bond between two atoms in which electrons are shared unequally. Oh no, not ionic. This is polar. An ionic is between a metal, I think. It makes an ion. Is it? I'm confused already. Where is it? Not shared equally, and nonpolar is shared equally. So is there such thing as polar covalent? I don't think that it exists. A polar covalent bond is a bond that exists between two atoms consisting of electrons that are unevenly distributed. I got a picture. I'm getting confused. Non-polar covalent and polar covalent. Non-polar bonding electrons shared usually between two atoms, no charges on atoms. So it's equally shared. But polar covalent means bonding electrons shared unequally between two atoms. So what does covalent mean? Covalent definition, chemistry. Covalent bonding chemistry is a chemical link between two atoms in which the electron pair are shared between them. What is considered non-covalent? Non-covalent does not involve the sharing of electrons, but rather involves more dispersed variation of electromagnetic between molecules. What is non-covalent again? I'm confused. It does not involve the sharing of electrons. So it probably does not exist then. If it's not sharing, then what the fuck is the point of it? Anywho, is a complete transfer of one or more. A covalent bond. The covalent bond is a type of bond. Which means that no, covalent bond is just saying that there's a bond happening. Because there's a sharing of electrons. Okay, and then this is the covalent bond rules. It's non-polar. That means they don't have this thing right here. Like this little sharing of like slightly negative, slightly positive. There's no such thing. If it's less than 0.5, because less than 0.5 means it just pulls it in so fast. Wait, non-polar means... What's the difference between non-polar and ionic now? I'm getting confused. Non-polar versus ionic. Okay. Non-polar, it's equally shared because no one side is overpowering the other, so they're equally sharing it together. Non-polar covalent. Covalent is a sharing of electrons. Just the word of it. Just the word of it is just sharing. Non-polar means it's not being overpowered by any side. Polar means it is by one side. It's being pulled. The bond. But it doesn't have enough electronegativity. That's why it's between 0.5 and 1.7. It cannot do it. It can't completely pull it, but it still has some energy to pull it a little bit, but not enough to completely rip it off and steal it. That's where ionic happens. Ionic is the complete transfer. That's how you have Na plus Cl minus. It just completely takes off the electron from sodium and gives it to chlorine, making a sodium chloride. And then it says something important here between 1.7. Where is it? So what happens? If the ends between if it's between 1.6 and 2.0, right here, if a metal is involved, then the bond is considered ionic. Because metals don't want the extra electron. It makes sense. They just want to give it away completely. They don't give a shit. Give it up. And if it's non-metals like gases, then it's covalent polar. It has this slightly negative, slightly positive. Because they're all strong. don't know. Polar Y. Non-metals. Non-metals involved bonds considered polar covalent. Why? I'm trying to understand why. Electronegativity charges here. Nope. I guess, whatever. Well, here it doesn't even discuss it. It doesn't even say what's between 1.6 and 2. It just says up to 1.7. Between 0.5 and 1.7, it's polar. Above 1.7, it's considered ionic. Okay, so they just abandoned that rule then. Why is there two different ways of saying it? I'll go with this one. Positive plus cation and is negative. Crystalline lattices, large organized arrays of ions. Okay. I want to understand the sentence right here. Relatively ionic bond is formed via the transfer of one or more electrons from an element with a relatively low ionization energy, means the minimum amount of energy required to get rid of it, to a high affinity that they want to take energy. So ionization energy is lose energy, lose electrons. Electron affinity want electrons. So low ionization energy means to make an ion, and ions want to steal it. So it's just saying it's the opposite. I want to be less of an ion. I don't want to steal electrons. I want to actually do the opposite. And this one's saying I want electrons, affinity. I want more. Give me. Intermolecular forces, hydrogen bonds. Dipole, and London dispersion. So these are hydrogen bonds. Anything with hydrogen, it will be considered a hydrogen bond. And it goes by strength. Okay, hydrogen bonds would be higher. I never knew that. Look how London dispersion was. It's called van der Waals forces. And oh, so it goes in between. Van der Waals goes between dipole and London dispersion. Push up dipole real quick. Dipole forces. So it's just with polar molecules.
My mom said take care of the birds.
I said no. How many pages do we do? 1, 2. I can get through this whole thing. Alright, I'm gonna get through this entire thing by the end of the stream. How long have I been streaming for? I've been streaming for the past... Started around 9 o'clock. 9:10. I started around 9:10. So just say 9, 1, 2. I was studying for 2 hours and I did this much. Nice. That's pretty cool. Still so much more though. How many pages is chemistry? 20 something, I think 27. And we only went through 2. Yeah, it's bad. So 2, and then it would take me 15 days to finish chemistry. It's not good. Dipole. How do I know it's dipole? Dipole force interaction. Is when two dipolar molecules interact with each other. So with the polar bonds, is it only polar molecules? Only in polar molecules, okay. And the London dispersion means London dispersion is a weak intermolecular forces between two atoms or molecules in close proximity to each other. So it always exists. What are some examples of London dispersion? Example of London dispersion forces interaction between two methyl CH3 groups. Another example is the interaction between the nitrogen and gas and oxygen bonds. You can see images. What? Another helium atom nearby that would have a dipole induced in it. So when they bond, so the electrons are attracted to the positive side of the electron element of helium, which means that now this helium's electrons now want to go to the left side, go away from that repulsion. So before there's no negative side and positive side, but after there's two of the same kind of helium, you have polarization because it's getting attracted. Now you have a region of equal amounts of positive and negative, which makes it a dipole, induced dipole. It made it into it. Okay. Sigma and pi bonds. This is organic chemistry. A single bond is a sigma bond. A double bond would be still a sigma bond, but it would be one pi bond. So sigma bond is just if there's a bond or not. Chemistry. Sigma bond is
In this video, I'm going to give you a brief introduction into sigma and pi bonds. A double bond contains one sigma pi bonds. So I'm going to use as formed from the overlap of atomic orbitals. The carbon is sp2 hybridized, and hydrogen has an s hybridization. So therefore, once we mix the s orbital with the sp2 orbital, that produces a sigma bond. So this is another sigma bond. So this one is formed from the overlap of two sp2 hybrid orbitals. So as you can see, this molecule has 5 sigma bonds. 1, 2,
Pi bonds.
3, 4, 5.
But it has one pi bond.
Now the pi bond
One, because it's double.
arises due to the unhybridized p orbitals that exist above and below the sigma bond.
What did it say?
Orbitals that arises due to the unhybridized p orbitals that exist above and below the sigma bond. So this forms the pi bond. And the sigma bond is in the middle. So now you can visually see how a sigma bond and a pi bond, how they look alike and how they differ. So all of these are sigma bonds. So in this molecule, we have 5 sigma bonds and 1 pi bond.
Pi bond looks like this. Pi bond looks like this. It looks cool. It looks like this right here. Like a tube. Like if a single bond looks like this, a pi bond will look like this.
So let's work on some problems
Okay, it's simple.
and determine.
Well, C has 6, so 1, and then 3. It would have 3.
So first, you want to draw the molecule.
Wait, would it have 3? No, 1, 6, 8. Yeah, it has to have octet. So 1, 2, 1, 2, 1, 2, 1, 2. So 3 triple bonds. So like this. H, C, C, H. This only has 2. It can only have 2. Hydrogen only can have 2. It can't have 8. It only has one electron. So it just needs 1 electron from the carbon. Carbon has 6 valence electrons. 6 valence. So 1 is already used from that. So now there's 5 left over. There's 5 left over from that. So they can combine that to make 10. So there's 10. 10, and then it's going to be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10. Wait, 6. So there's 2. Okay, it's 2 carbon molecules. Two carbon elements. That's 12 valence electrons. Plus the 2 from the hydrogen. That gives us 14 total. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. What is something is missing here? One, 2, 3, 4, 5, 6. No, it has 5. It has 5. So now we have less 12. So 12 here. 12. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. What? I'm confused.
With symmetry in the middle. Now, how many sigma and pi bonds?
Valence electron. 4. Is it 4? It's 4. I'm dumb. Oxygen has 6. Sorry. So carbon has 4 times 2 carbons, which is 8, plus that 2 from these hydrogens, which is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is the, satisfies the octet rule because there's 2 hydrogen, 2 for hydrogen, and there's 1, 2, 3, 4, 5, 6, 7, 8 for this carbon. So there's 8 around it, and there's 8 around this one too. 1, 2, 3, 4, 5, 6, 7, 8. So this would have three sigma bonds, and it would have, so pi bond would be 1, and there's 3, so there's one more, so there's 2 pi bonds
present in this molecule. Pi bonds. So we
2
have 3
and 3.
sigma and 2 pi bond. Driven pi bond are only. So we could see that we
That's not a bond.
have 1,
1 2 3.
2. So that's the number of sigma and pi 2.
1 2 3 4.
So having that knowledge, we can 2 and pi sigma bond, and each double bond contains 1
1
pi
2.
bond. That's all. So I'm going to give you a more complicated structure. Determine the number of sigma and pi bonds in this compound.
1 2 3 4 5 6 7.
So
1 2 3 4 5 6 7 8 9 10 11. 2 3.
all you got to do is just count the number 4. That's 2 bonds.
11. 1 2 3 4 5 6 7 8 9 10 11.
So we have
Simple. Formal charge. This is easy. Formal charge is the amount of valence electrons plus the valence electrons. That's where you get from memorization, valence electrons, how much valence electrons, and the dots would be the non-bonding electrons. Yeah, that would be the on the outskirts, like how it was right here. Right here.
found in C.
These are non-bonding electrons. So 1 2 3 4. What is the formal charge of oxygen here? Formal charge would be the 6 valence electrons. We just know this from a fact. We know that it has 6 valence. I'm not looking at anything. I just know it. 6 valence electrons. No. Oxygen has 6 valence electrons. Minus, this is where we start looking at the molecule. 1 2 3 4. 4 non-bonding electrons. Minus 2 sticks, which is 2 bonds. So it would be 0. It would be perfect. Formal charge of 0. You want it to be 0. So there's 3 rules to a perfect Lewis structure. One is formal charge as minimal as possible, or just 0 of 0 of 0, and 2 would be octetable. You want it to fill the octet, which would be, example would be 2 or 8. Of course, the first for hydrogen would always be 2, but for everything else would be 8. 3 rule is what's the other rule? You can only have triple bonds? Up to triple bonds, yeah. Whatever. You get the point. Next is formal charge we do. What is that? Who cares? Valence shell electron repulsion is a separ valence shell electron pair repulsion theory. SP, this is a hybridization. This is just all memory. There's no point in really learning this. It's all memory. You look at the thing. SP. So right here, let's look at this molecule here. We have this one right here. So these are electron high electron regions. 1. So for, let's just say we have to choose 1. So let's choose carbon. So there's 1 2 3. It'll be sp2. S is 1, and then there's 2 p, so that'd be 3 of them. sp2 would be C. That's the hybridization for carbon, center carbon. For oxygen, it would be 1 2 3. 3 sp2. But when you want to look at the geometry of it to see if it's linear, trigonal, planar, tetrahedral, you have to look at, now that we know that there's 3 electron regions, 1, 2, 3, we also have to know there's non-bonding electron regions, so that'd be 2 of them and 1 bonding. So lone pairs, so for 3, 2 of it are lone pairs, 1, 2, and that would mean 1 bond pair. See how they're all equal to 3 when you add them up? 3, 3, 3, because there's 1, 2, 3 regions. So this would be, it would be considered linear, the molecular shape, but it would be trigonal planar geometry. How does that make any sense? Linear, trigonal, planar. Trigonal, planar. I love organic chemistry. It's so interesting. Oh, it's just trigonal pure. It's not pyramidal. It's planar. Planar means on the same plane. And it's linear. See how here is bent? It's bent, not linear. This is linear. How is this linear? I'm so confused. You get the point. You can always look at this. You can refer to it. It's never memorization. You just have to know how it works. You just know then from that, looking at one of these, you can tell the bond angle. And then sometimes they ask you slightly less than 109.5 or slightly less than that, slightly less than that, slightly less than that. You only find that out if it has lone pairs. So there's lone pairs, it would be less, slightly less, slightly less. For this, it won't be slightly less, if I remember correctly. So this is easy. Equivalent mass. Everything else is non-visual. This is just naming ions. Okay. Equivalence normality. Mass of an acid that yields 1 mole of H plus, or mass of a base that reacts with 1 mole of H plus. Do I want to look at this? This looks interesting. But I just need to use the bathroom. I just need to go. I'm a little sleepy. We'll resume this. Oh, rate laws. Radioactive decay. What is this? I don't remember this. Arrhenius bullshit. What is that? Exergonic, endergonic. Hydrolysis, neutralization, combustion, decomposition. I don't know what the combination is. Double displacement. I don't forget that. Single displacement. What is that? Displace means to take away from it and place someone else. Kinetic. I'm glad I paid attention. These are the equilibrium constant based on the rate law. Rate's the rate law. Rate law right here. This right here. A. What is it? Yeah. I'm confused. How is this the same thing? I should have paid attention. I don't know what the reaction quotient is. I've heard of it though. I've seen it. And then everything else is just easy. This is just bullshit. I'm glad it's not something like it gets harder. That he just randomly put everything. Try to make it organized. Solubility rules. Galvanic cells, this is the energy levels. IUPAC names, that's organic chemistry. This is organic chemistry. Okay, so this is good that I'm learning organic chemistry. Redox reactions. Oh, garbage. Those are shit. Alcohols. This is just. I'm hoping I know what this is. First primary carbon, secondary carbon, or some shit like that. It means it's a carbon connected to two other carbons, if I'm correct. Yeah, it gets interesting. Trees just so much. What is ring strain? I've never heard of this. Oh, it's from a ring. Okay. Amides, esters. God damn it. There's no way I have to memorize this though. It makes no sense. Is this biology? This is organic chemistry. Okay. Chromatography. I know chromatography is distillation. All of this, I know this. Spectroscopy. Damn, I was actually prepared from school. I was actually taught most of these things. Peptides, proteins, amino acids, phospholipids. Yeah, this is all easy. This is organic chemistry? Really? It's that easy? Except hydrophilic hydro. This is a micelle. It's a micelle. Okay. Well, amending machine is pleasant. I learned. Let's just say 15%, 10% learn, and then the rest were just remembering the stuff I already knew. So, peace.